So in this section, we're going to start looking at limiting reactants. What is a limiting reactant? Well, what if we're given amounts for both of the reactants in a reaction? Let's say we're doing a reaction and it has two reactants that need to come together and react to produce whatever products we're going to make. This can be for two or more, but we're going to focus on two reactants in this section. If we're given amounts for both reactants, how do we decide how much product we can make? In this case, one of the reactants will be completely consumed or reacted, whereas the other reactant will actually be present in excess, meaning some reactant will be left over. The reactant that limits the amount of product that can be made is known as our limiting reactant. Now, you could argue that both reactants will react in the exact ratio that they will both produce the exact amount of product we have and nothing will be left over. And yes, we could calculate how much that is needed to make exactly that happen, to have the exact number of moles we need of reactant A, the exact number of moles we need of reactant B to be able to produce how much C we want. But we don't usually do reactions that way. Multiple reasons. Sometimes it's just doesn't make sense or conducive to measuring things out that way. It could be that, just because we say all of a reactant's going to go a certain way doesn't mean that reactants are always 100% efficient. There's a lot of things that go into a reaction. So most often when you do a reaction, one reactant will be present in a specific amount that's going to limit the amount of product that can be made. It's the reactant that runs out first in the reaction. The other reactant will be present in excess. So that's what we see in the picture up here. We've got your limiting reactant, H2, your excess reactant of O2. So H2 plus O2 is going to make water. And we see here that the H2 comes in and it reacts and it makes water. But we have excess of the O2 left over. We have one extra molecule of O2 left over. It's left over because there's no more hydrogen that can react with it. When I look here, I've got 2, 4, 6, 8 hydrogen atoms or 4 hydrogen molecules. One hydrogen molecule will react with 1/2 of an oxygen molecule to produce one water molecule. So that means, in theory, if I look at all the hydrogen, I can make 1, 2, 3, 4 water molecules. 1, 2, 3, 4 are in fact made. If I look at oxygen though, 1/2 of an oxygen molecule goes into making water. I can make 1, 2, 3, 4, 5, 6 water molecules. That's an excess because I don't have enough hydrogen to actually make all of that. So common questions you need to ask yourself and think about when you get to stoichiometry examples. And again, this can continue on. We can continue doing stoichiometry problems like this in the next chapter. We look at solutions, when we look at thermochemistry, which is energy, gas laws, etc. This can all come into play with limiting reactants. What I want you to ask yourself is, which chemical is my limiting reactant? How much of my excess reactant remains after the completed reaction? And how much product can be formed? You must use the limiting reactant to answer that last question. The amount of product formed is limited by the amount of limiting reactant. So we do have a series of definitions here that you need to be comfortable with. Again, chemistry is a foreign language. You are learning lots of definitions this semester. Your limiting reactant, we also call this your limiting reagent. And this is the reactant that is completely consumed or used up in a chemical reaction. It does limit the amount of product that can be produced. So the two ways you're going to hear limiting reactant discussed is completely consumed in a reaction and limits amount of product. Those are both correct terms, and truthfully, they're both required to accurately describe a limiting reactant. So if I asked you to define a limiting reactant, I would expect both the reactant that's completely consumed or used up in a chemical reaction and the reactant that limits the amount of product made. For a complete answer, I would expect, or a complete full credit answer, I would expect both of those answers because they each make up part of the definition. What is your reactant in excess? Reactant in excess is any reactant that is in a quantity greater than is required to completely react with the limiting reactant. We saw in the previous example was that oxygen was in excess. what is your, and then we see in the picture here, we've got hydrogen gas and chlorine gas reacting to form HCl and H2. We see here, if we were really just trying to form HCl, we've got 4 chlorine molecules, 1, 2, 3, 4, 5, 6 hydrogen molecules. Well, if I'm trying to form HCl, I have excess H2 here. Your theoretical yield. Theoretical yield is the amount of product that can be made in a chemical reaction. This is based entirely on your limiting reactant, because once the limiting reactant runs out, I cannot make any more of my product. So the limiting reactant, you use that to figure out how much product can you actually make. Your actual yield, on the other hand, is the amount of product that's produced in a chemical reaction. Now, you would love if your theoretical yield and actual yield matched. The truth of the matter is, they won't match. Do experiments. Side reactions happen. You lose product along the way during purification steps or even just during the reaction. Some reactions don't go to completion. There's a multitude of reasons why your actual yield will not match your theoretical yield. To measure the efficiency of a reaction, we have 2 different things we can do. We can calculate percent yield and we can calculate atom economy. More commonly, what you're going to see is calculation of percent yield. Percent yield looks at how much product did you obtain from a reaction in percent form. It's calculated by taking your actual yield divided by your theoretical yield and multiplying this value by 100%. So percent yield only looks at how much did you actually make of your desired product divided by how much did you theoretically believe you could make of that product. Atom economy is a more recently developed term. It's a green chemistry concept. Green chemistry, the first major book in the field was published in the late 90s, I believe 1998. And green chemistry is more of a sustainable or environmentally conscious way of thinking about chemistry. And so the focus of it is really getting scientists to think about what are you doing, how can you do something with a more sustainable mindset, and can we kind of make this reaction work a little bit better for our environment. So whereas a percent yield just looks at how much did you actually obtain versus how much could you have obtained based on your limiting reactant, atom economy asks you how many atoms in the reactants become atoms in the products. So it's just looking for a different spin on it. It is calculated by taking the molecular weight of your desired product and dividing it by the molecular weight of all of the reactants that went into the reaction to begin with, multiplying this value by 100%. So it doesn't really care about how successful your reaction was in terms of making your desired product. It's instead interested in how much of your desired product. So remember, law of conservation of mass, everything that goes in must come out. Atom economy is looking at, we put all this in, depending on what comes out, what do we actually want that's coming back out? Whereas percent yield is really looking at, okay, this is how much I should be able to make, how much did I make? So atom economy, looking more on the side of how sustainable or how green, how efficient is this reaction in the fact of what goes in must come out kind of thing. Whereas percent yield is looking more at the fact of, this is how much I should have actually made, how much did I could have actually made, how much did I actually make? So how much could I theoretically make versus how much did I actually make? They're both looking at efficiencies, but from different perspectives. So let's go ahead and work a limiting reactant problem. Chick-fil-A. If you have not had Chick-fil-A, I promise you will, if you like chicken at least, you will eat there this fall since it's in the blue. Students eat there, well, kind of frequently. And a very common staple of Chick-fil-A is their Chick-fil-A sandwich. The recipe for a Chick-fil-A sandwich is 2 pieces of bread, 1 piece of chicken, and 2 pickle slices. So that's what one sandwich contains. Now, most of us look at this and like, okay, put 2 pieces of bread together, a piece of chicken, and a pickle. Cool. We can write this as a balanced equation though. We're going to use BR to represent bread, CHI to represent chicken, PIC to represent pickle, and SAND for sandwich. So I've got 2 breads plus 1 chicken plus 2 pickles gives me 1 sandwich. And that is balanced. That is exactly what goes into making 1 sandwich. So, how many sandwiches can you make with 8 pieces of bread, 5 pieces of chicken, and 10 pickle slices? Most students will look at this pretty quickly and say, okay, 8 pieces of bread, this could give me 4 sandwiches. 5 pieces of chicken, this could give me 5 sandwiches. And 10 pickle slices, this could give me 5 sandwiches. So they're going to say, we can make 4 sandwiches. And that's correct. But we can also do this with stoichiometry. So let me go ahead and move our balanced equation. I'm going to move it up here so we have some room to work. And I want you to do this, though, with stoichiometry instead of just intuition by putting together the sandwich. What do I mean by that? In order to do a limiting reactant problem, you need to do multiple steps. So what we're going to do here is we're going to figure out how many sandwiches could I make based on each ingredient I have. So the number of sandwiches, knowing I have 8 pieces of bread. Convert this to sandwiches. Every 1 sandwich takes 2 pieces of bread. This makes 4 sandwiches. Number of sandwiches based on my chicken. I have 5 pieces of chicken. 1 sandwich contains 1 piece of chicken. So I could make 5 sandwiches. And lastly but not least, my pickles. Number of sandwiches equals 10 pickle slices. 1 sandwich contains 2 pickles, so I could make 5 sandwiches here. So as we already described, under these conditions, I could make 4 sandwiches. And that is, of course, based on this here, meaning that my bread was my limiting reactant. So what's your limiting reactant? The bread, because I can only make 4 sandwiches because of bread. What is your access reactant or reactants, and how much access is there? Well, I have an access chicken, and I have access pickles. I have 5 pieces of chicken, but I can only make 4 sandwiches, which means I have 1 piece of chicken left over. I have 10 pickles, but I can only make 4 sandwiches, which means I have 2 pickles left over. We're going to do the same thing as this, except that we're going to do it with chemicals instead of Chick-fil-A sandwiches. So I want you to follow this chart when you're doing reaction stoichiometry. I think this will actually help you out a lot while you're working through this. So step 1. Convert what you are given to moles. We always convert to moles. It's just kind of our favorite thing to do. It's our safe thing to do, and it gets us to the right step. So make sure you are converting to moles. Again, like we've talked about before, converting to moles is done because it's what gives us, it's how we can actually compare apples to apples. We can't do it without that. Step 2, I want you to ask yourself a question. Ask yourself, if you use up all of one of your reactants, how much of the other reactant would you need? Step 3, answer question number 2 using your mole ratio. Step 4, ask yourself, do I have it? Do I have enough? to solve to do what I found for the answer in step 3. Step 5, you're going to assign labels, limiting and access. One of your reactants will be the limiting reactant, one will be your access reactant. And step 6, use your limiting reactant to solve your original stoichiometry problem. This method is different than your textbook, but this is the method that we will use whether you're in my class or Dr. Fry's class. So this is the one that you guys need to be comfortable with in this course. In Gen Chem here, you need to be able to use this method. This is the method we prefer. We find students do better with it, so you need to follow this method. So just to kind of keep our directions up here in the back of our mind, we're going to solve this question. In a commercial process, nitric oxide, NO, is produced. What mass in grams of NO can be made from the reaction of 30 grams of NH3 and 40 grams of O2? So I've got 30 grams of NH3 and 40 grams of O2. And I want to know how much NO can I make in grams. And I'm definitely not going to have enough room on this slide, so I'm going to have to write some stuff, work through steps, erase, and move backwards and forwards like that, but we'll get there together. So please, if you need to, make sure you pause the video. I'll try to make sure to stop before I erase things just to let you guys know you're going to have to pause quick. But step 1, convert what you are given to moles. So step 1, we need to convert our reactants to moles. Number of moles of NH3 equals, I've got 30 grams of NH3, and I'm going to convert this to moles. 1 mole of NH3 is equal to 17.03 grams of NH3. The molar mass of NH3 is 17.03. This equals 1.76 moles of NH3. Do the same thing with your oxygen. Number of moles of O2. I've got 40 grams of O2 times 1 mole of O2 to 32 grams of O2. This gives me 1.25 moles of O2. So go ahead and pause if you need to write this down. I'm going to rewrite what I've given in moles underneath my reaction up here, actually right above my reaction up here. So I know that I have 1.76 moles of NH3 and 1.25 moles of O2. I'm going to write them there so that we can continue to work on this slide and not completely jumble everything up on you guys. So step number 2, how much do I need of a reactant if I use up all of the other one? How do I answer this? Well, I'm going to say, how many moles of NH3 do I need to completely react all of my O2? And why do I pick NH3? Just because it's first. It doesn't matter. I could do it the other way too. I could say, how many moles of O2 do I need to completely react NH3? I'm just going to do it this way because NH3 was listed first. So number of moles of NH3 needed to completely react the O2. I know I have 1.25 moles of O2. How many moles of NH3 does it require to completely react all of this O2? I see the ratio is 4 moles of NH3 to 5 moles of O2. This gives me 1.00 moles of NH3. Now, step 3 says, so I asked the question. Step 3 is answering the question using mole ratio. So this covers step 3. This is my answer using the mole ratio. Now, step 4, ask yourself a question. Do I have enough? What do I mean by that? I'm saying if I want to know how much NH3 I need to completely react all of my O2, do I have enough? Ask that question. The question is yes, we do have enough. We need 1 mole of NH3 to completely react all of the oxygen. We have 1.76 moles available. So I can now assign labels of limiting and access. Because I know I have more than enough NH3 to complete this calculation, this means my NH3 is in access and my O2 is limiting. Now, I lucked into that, I promise. I did not purposely solve for using NH3 or using the amount of oxygen to solve for NH3. It was completely randomized just because it was first. That does not mean it's always going to be that easy. So please pause if you need to write this down, because I'm going to erase this to write down a little note down here. So the trick to this is, if you do not have enough, say this said that I needed 2 moles of NH3. I don't have enough for that. So if you do not have enough, you can still determine your limiting and access reactant. In that case, whichever one you don't have enough of is your limiting reactant. You just may need to recalculate to determine your final yield and product. But again, if I had solved this, and instead of 1 mole of NH3, it told me I actually needed 2 moles of NH3, in that case, because I knew I didn't have enough NH3, the NH3 would have been my limiting reactant, whereas my oxygen would have been an access. But instead, it worked out conveniently, and I did have enough. Again, pause if you need to write down the words, because I do need the space. So, I've assigned limiting and access labels. I am ready for step 6. Use your limiting reactant to solve the original stoichiometry problem. So, since O2 is the limiting reactant, we use it to determine the amount of product produced. I want to know the number of grams of NO that I can make. I know that I have 1.25 moles of O2. 4 moles of NO are produced for every 5 moles of O2 consumed. The molar mass of NO is 30.01 grams per mole. And it's always good to double check, make sure your units are canceling out. And this gives me one second, I forgot to write this out. And I apologize. So 1.25 times 4 divided by 5 times 30.01. I apologize. This is actually easy math, but it's really late, and my brain cannot think that fast. 30.01 grams of NO that has been produced. So if I react, what is it? Let me check. Sorry. 30 grams of NH3 and 40 grams of O2, I will produce 30.01 grams of NO. In this example, in the balanced equation below, how many grams of solid iron can be formed if 50 grams of iron 3 oxide reacts with 10 grams of carbon monoxide? What is the excess reactant and how much excess remains? Excuse me. So this problem's going about it a slightly different way. It's still a limiting reactant problem. But in this case, I'm not asking you what your limiting reactant is or even how much product I can make. What I'm really asking you is how much excess reactant remains. And this is probably the most difficult problem for students. This is the one most commonly missed. Students don't like these problems. They don't like figuring them out. If you follow the method, then I believe you'll get to the right spot. So please follow that 6-step method we talk about. I'm going to do a little bit faster. I'm not going to do it as slowly in each individual step through this example, but I will try to talk through it a little bit more in detail, at least on this video. But you need to practice excess reactant problems. There's some in your homework, there's some in your textbook, there's more additional at the end of this PowerPoint. Please practice them because they're important. We do use excess of one reactant most of the time. Sometimes we need to. Sometimes, you may be using a reactant that we need a little bit of access with because of side reactions or something else. Like all kinds of things can happen in a chemical reaction. But we don't want to be wasteful either. So we want to know how much is actually remaining after the fact. Did I completely overdo it? Did I have, a kilogram of excess? Or did I have 15 grams of excess? It's all relative to the reaction we're doing. So, excuse me. In this example, first, by context, I know this is a limiting reactant problem because I'm given amounts for 2 or more reactants. So when given amounts from 2 or more reactants, this is a limiting reactant example. And in this chapter, we're really focusing just on moles and grams, but we can also do this with volumes. We can do this with concentrations. There's some examples with volumes in the problems at the end. You're going to see it in other chapters as well. You can do it with concentrations, which we'll cover in chapter 5. We can do it with gases. We can do it with energy. There's a lot of times we can do this, but you need to recognize if you're given amounts of 2 or more reactants, it is in fact a limiting reactant problem. So now let's look at the question really quickly again. In the balanced equation below, I want to know how many grams of solid iron can be formed if 50 grams of iron oxide reacts with 10 grams of CO. So I've got 50 grams of iron 3 oxide, I've got 10 grams of carbon monoxide, and I want to know how many grams of iron can be reacted. So that's the first question. How many grams of solid iron can be formed if I'm reacting 50 grams of iron 3 oxide with 10 grams of CO? The second part of this question is, what is the excess reactant, meaning the identity of the excess reactant, and how much excess remains? Another thing to note here, I still have students that get it wrong, so I just want to make it very abundantly clear. In the past, I've asked problems where I just give a reaction like this. I don't say how many grams can be made. I don't say how much excess can be left over. I have used this exact question before and just asked students, what is your excess reactant? And I'll make it a multiple choice question. I'm not saying I'm doing this to you guys. I'm just saying I've done it before, this exact question. And that's why I put it in your notes. I would give this question saying what's the identity of your excess reactant or your limiting reactant, whichever. And I would give 1, 2, 3, and 4 options. And maybe a quarter, maybe 25% of the class would pick either C or D. By definition, they cannot be your excess or limiting reactant. So if I ever, in this question, the reason I specify that in this question, I say, what is the excess reactant? Well, it has to be one of these two. And I know that seems almost, some students told me that seems like almost like, well, foolish or intuitive, But when you're in the throes of an assessment and you're stressed out, sometimes your mind just doesn't work that quickly. So please think about definitions in this class. Definitions can guide you back to the right spot. So there is actually two different methods I can use to solve this. One is more similar to the way your textbook does it. One is more similar to the way I taught you following through that 6-step method. I'm going to show you both. I will tell you that the first method I'm going to show you often is the one that if you're, I don't know how to say this, if you're just kind of stronger in this material, you'll be fine with either method. If you find yourself struggling or trying to remember the next step or just kind of being overwhelmed with the material, please follow the second example I do, and which is the one that follows that 6-step method, because that 6-step method will just get you there faster. So the first way, which is closer to the way your book does it, is you ask yourself, if each one is limiting reactant, how much of my product can I produce? So if Fe2O3 is the limiting reactant, Lr meaning limiting reactant, how many grams of iron can I produce? I'm starting with 50 grams of iron 3 oxide. I got to convert that to moles. And when I add up the molar mass of iron 3 oxide, I find it to be 159.7 grams of iron oxide per 1 mole of iron oxide. Now, this is a balanced equation. It does tell me in the question it's balanced, so I don't have to worry about that. Now I can go ahead and convert to moles. 2 moles of iron for every 1 mole of iron 3 oxide. So for every 1 mole of iron 3 oxide reacted, I produce 2 moles of iron. Convert this to grams of iron, 55.85 grams of iron to 1 mole of iron. This gives me 35.0 grams of iron. I'm going to do the same exact thing for this carbon monoxide. So if carbon monoxide is my limiting reactant, how many grams of iron could I produce? Starting with 10 grams of carbon monoxide. Convert that to moles. 1 mole of carbon monoxide is 28.01 grams of carbon monoxide. Convert that to moles of iron. I'm producing 2 moles of iron for every 3 moles of carbon monoxide that's reacted. Now convert that to grams of iron. 55.85 grams per mole is the atomic weight of iron. And this gives me 13.3 grams of iron. Now what I can do is I can compare these two numbers and I see which one makes less iron. This is why this other method is a little bit better for students if you kind of get lose track on where you're going, because in this one, you have to remember, convert both, then compare them, and we're still not done. We haven't even figured out the access problem yet. But when I look at these, I see that the iron 3 oxide could make 35 grams of iron, while carbon monoxide could only make 13.3 grams. What that means is that carbon monoxide is my limiting reactant. This means I can only make 13.3 grams of iron. But I have not answered the second question yet. The second question is, what is the access reactant and how much remains? Well, I know right now that my limiting reactant is CO, or carbon monoxide. My access reactant is iron 3 oxide. I know I can form or produce 13.3 grams of iron, but I do not know how much excess remains. So the way to find the excess in this method is, I need to make space, but I need to remember these two numbers. So I'm going to keep what's highlighted for just a sec there. So with this method, what you need to do is take the difference between these two numbers. So 35.0 grams minus 13.3 grams. And I did not write this out because I solved it the other way for this. So 1 second while I find my calculator. This gives me 21.7 grams of iron. That means that the iron 3 oxide could have made 21.7 grams of iron more than the carbon monoxide could. But I need to know how much that is in iron 3 oxide, not iron. So then I take that value, 21.7 grams of iron, convert that back to moles of iron, convert that to moles of iron oxide, and convert that to grams of iron oxide. And just because I didn't do it in the last example, but for practice, remember, it's always good to go through and just kind of make sure that everything's canceling out. I'll do it randomly when I'm doing example problems, but until you get comfortable, you should probably continue to do that. So 21.7 divided by 55.85 divided by 2 times 157.9. I get an answer of 30.7 grams of iron 3 oxide rather. That means I have about 31 grams of iron 3 oxide specifically left over. Again, this is the longer way to do it, and that's totally fine. The faster way, so the first part of it, figuring out the limiting reactant and how much iron you can produce. Doing it this way, the longer way that I just did it now, this way that your book does it, perfectly fine. But this method here to find out the excess reactant, this is probably the most missed thing in this class. I know I say all these things are missed. There's a few major things that are missed, and this is one thing. Students never are able to follow this process backwards. So this is where that 6-step method, although it seems long, definitely benefits the student, because it can tell you the limiting reactant very quickly. It can quickly tell you how much the excess reactant, how much excess remains, and then you can just do one more stoichiometry step to figure out how much you could produce of that product. So I'm going to erase this stuff and show you what I mean following that method instead. So please pause the video if you need to write any of this down. So if I want to do method 1, this is where we convert both species to moles, but then we ask ourselves, how much of one do I need to react all of the other? Again, I'm going to do this in one fell swoop. Because we already know that carbon monoxide is the limiting reactant, I want to know how much iron 3 oxide is needed to react all of that carbon monoxide. If I didn't know that, you can still do this in multiple steps. I could still say, number of moles of carbon monoxide, number of moles of iron 3 oxide. I just don't have them calculated out, so I'm not going to write them out, but I can still follow the full step. The other thing I can do is I can just plug it all into one stoic question straight through to figure out how many grams of iron 3 oxide would be needed to react with all of the carbon monoxide. It's still going to tell me if I have enough or not. What do I mean by that? Well, let's look. Number of grams of iron 3 oxide that I need to react all of my carbon monoxide. I've got 10 grams of carbon monoxide. Convert that to moles. 1 mole of carbon monoxide is 28.01 grams of carbon monoxide. Now that I'm in moles, I can convert to moles of iron 3 oxide. 1 mole of Fe2O3 to 3 moles of CO. Always check yourself. Grams of CO have canceled, moles of CO have canceled. Now I've got moles of iron 3 oxide. I can quickly convert to grams of iron 3 oxide. I know there's 157.9 grams of iron 3 oxide for every 1 mole of iron 3 oxide. This comes out to 19.01 grams of iron 3 oxide. What does this value mean? What does this 19.0 mean? This means in order to react all 10 grams, I need 19 grams of iron 3 oxide. Do I have enough? Yes, I absolutely have enough. So therefore, I know right now that my iron 3 oxide is my limiting reactant. I also know I can quickly, much quicker now, determine how much of my excess reactant remains. It's actually a lot easier to do it this way than it was to do it the longer way. So now I know I need 19 grams of it. So if we need 19.0 grams of iron 2 oxide to completely react (10 grams of carbon monoxide), and we know we're starting with 50 grams of Fe2O3. We will use 19 grams to completely react all of the carbon monoxide, so therefore there is 31 grams of Fe2O3 left over. Now, we calculated before it was 30.7. That's just round off error. That's pretty much the same thing. You're at the same point. But this was a much quicker way for us to find the excess. Now, some students will be like, but then I still don't know how much iron I need. This is true. But because we now know that carbon monoxide is absolutely for sure our limiting reactant, we could just go ahead like we did before and say number of grams of iron that can be produced from 10 grams of carbon monoxide. Convert that to carbon monoxide. Convert that to moles, moles of iron. I apologize for all the background noise. I am recording these from my childhood home, and I live on a main drag. But I'm trying to get these videos done for you guys so that I can focus on you guys throughout the semester instead of getting these done. But I know, because I know how helpful these can be to you guys when you're trying to study and trying to remember a concept. And so if we calculate this through, we find again that we can make 13.3 grams of iron. So this is kind of a condensed way of doing it, the second method, or the method I taught you above, the method I taught you up here, this step 1 through 6. I still find, even though trying to remember those 6 steps can be difficult, and I'm condensing steps into multiple points here, I find overall students do better with this method, with the 6-step method, even if you follow it 1, 2, 3, 4, 5, 6, or if you know how to combine them like I've done here. I find students do better solving the problems this way than they do if I do them the way the book teaches it. So I'm not going to insist you do it either way. I know like other people will insist that it's done a certain way. I'm not going to insist that it's done either way, but I will tell you students get it right far more often if they follow that 6-step method and not the textbook. Let's work one more example. What is the limiting reactant in the balanced reaction shown below? If 18.1 grams of ammonia, so I've got 18.1 grams of ammonia, reacts with 90.4 grams of copper 2 oxide. So here, this is one of those questions I was telling you about that is just asking for what is the limiting reactant. This means what is the identity. This is not asking for amount. I honestly, in this question, could care less how much is actually made. It's not asking me that question. So I'm going to do it both ways again. I'm going to do it the way that follows that 6-step method, and I'm going to do it the way where we just compare the two species. Let's go ahead and do the 6-step method first, because that is the way, again, I recommend you doing it. So I want you to ask yourself, how much ammonia is required to completely react all of the carbon 2 or copper 2 oxide? Now again, you could say it as how much copper 2 oxide is required to react all the ammonia. I don't care which way you do that. I just do it this way because ammonia is listed first. Like, that's it. That's the only reason. And my brain reads very linearly, but it doesn't matter. So I want to know number of grams of ammonia if I want to react 90.4 grams of copper 2 oxide. So first thing I need to do is convert that copper 2 oxide to moles. I look it up and I figure out that the molar mass of copper 2 oxide is 79.55 grams. At this step, this cancels out my grams of copper 2 oxide. Now I can go ahead and use my balanced equation. You should always check this reaction is in fact balanced, so we can keep using it, but make sure that your reaction is balanced because they won't always be. Multiply this by 2 moles of ammonia to 3 moles of copper 2 oxide. Because I see in the balanced reaction, for every 2 moles of ammonia, 3 moles of copper 2 oxide are reacted. This cancels out my moles of copper 2 oxide, and I have moles of ammonia. So now I can convert to grams of ammonia, 17.03 grams of ammonia to 1 mole of ammonia. Gives me 12.9 grams of ammonia. So what is this telling me? This is telling me I need 12.9 grams of ammonia to completely react all of my copper 2 oxide. Do I have enough? Ask yourself, do I have enough? And the answer to this question is yes. I have 18.1 grams. Therefore, copper 2 oxide is in fact my limiting reactant. So this one kind of throws students off because students will try to do it by brute force and they'll be like, oh, 18.1, 90.4. Clearly ammonia is going to be the limiting reactant. No, ammonia is a really small compound, so it has a pretty small molar mass. And with only 2 ammonias reacting with 3 copper 2 oxides, we see that it is actually flipped here. The ammonia is actually our excess reactant. So again, this is the way I recommend you doing it. I'm going to show you the other method just in case you're more comfortable with it and you want to follow what the book does. But this is the way I recommend it because it's going to quickly tell you, you calculate how much could you have made or how much do you need to react it, and then ask yourself, do I have enough? If this value here had been greater than 18.1, we would have known that ammonia was our limiting reactant. Because it's smaller than 18.1, we know that ammonia is actually our excess reactant. Go ahead and pause the video if you need to keep writing. I'm going to go erase everything and show you the other method that follows what your book does. So the other way to do it is to calculate for both species. What do I mean calculate? I mean determine, pick either one. Determine how much product you can make from each reactant. This throws students off. First of all, you have 3 different products. Which one do you choose? Doesn't matter. It's all a stoichiometric relationship. Pick any product. The other thing is, because I don't actually care how much I'm making, I'm going to stop at moles. I'm going to say determine moles of any product. Because the moles relate back to that mass, and it's not, as long as I make the most moles of something, whichever reactant makes more moles of a specific product is going to make more grams of that same product. So I'm not going to bother converting all the way to grams for any of my products because it just takes time. Instead, I'm going to stop at moles. And because N2 is first, I'm just going to convert to that. So let's say, how many moles of N2 can I produce if I completely consume 18.1 grams of ammonia? Convert this to moles. I see I produce 1 mole of N2 for every 2 moles of ammonia consumed or reacted. And this would produce 0.531 moles of N2. Now check for the copper 2 oxide. How many moles of N2 can I produce from 90.4 grams of copper 2 oxide? I need to convert this to moles. So I know again, the molar mass here is 79.55 grams of copper 2 oxide per 1 mole. I'm producing 1 mole of N2 for every 3 moles of copper 2 oxide that is consumed. And this will produce 0.379 moles of N2. So as before, I compare these two numbers. I see this number is smaller, which means I see that the copper 2 oxide produces less N2. Therefore, copper 2 oxide is my limiting reactant. Again, this is just the other way to do it. It's the way your book does it. Students just tend to mess this one up more often, comparing the two reactants to each other just to keep students more on the right track, especially if you're dealing with excess reactants. I don't care which one you do, practice these problems. Practice more of them. When you get into chapter 5 in solution chemistry, practice them there. Limiting reactant and excess reactant questions and calculations come through your entire chemistry career. Whether you're stopping at Gen Chem, going through organic, or going higher up, you will do these problems again. So please, please, please practice these and become comfortable with them, because they are the ones that are going to trip up the students. And that's not our goal. It really isn't our goal to trip you guys up, I promise. Our goal is for you guys to master the material to a level where you can be successful and communicate in our world. We want you, I'm not saying you have to be perfect at it, but I want you to be able to communicate as a scientist. And this is part of what is involved in that communication, is learning how to calculate and how to do these things so that you're making efficient reactions.